In this video, we're going to talk a little bit about some properties of derivatives for vector functions that are going to be really nice shortcuts to help keep in mind. All right, let's take a look here at how these different rules work, and we have them summarized here in this theorem box. Keep in mind that we're going to need to make sure that we actually read all the words on the page. You already know if, again, you jumped ahead and started looking at 1 through 6 without reading all the other stuff. So let's start right from the top. Suppose here that I have u. U is a vector function. It takes in real numbers, spits out vectors with 3 components. Same thing for v. Okay, so these are vector functions, and we're going to assume they're differentiable vector functions. I can find their derivatives. We'll assume that whenever c pops up here, it's a scalar, and we're actually going to assume that f is another function here, but it doesn't produce vectors. It's like a regular old Calc 1 function, where you plug in a number, and you just get back a regular old number at the end. If you have these things defined in this way, there are some really nice properties that pop out, and a lot of these should be very similar derivative properties that you remember from Calc 1. Take a look here at number 1. If you want the derivative of a vector function plus another vector function, you can calculate that by actually just doing the derivative of each of the vector functions individually. That should hopefully sound familiar. Number 2 should hopefully sound familiar as well. If you want the derivative of a number being multiplied to a vector function, you can instead put the number to the side and take the derivative of the vector function first, then multiply the number on after. We do this sort of stuff all the time with regular functions, like if I had something like 3x to the 4th, and that was a function and I wanted to take its derivative, we often think about leaving the 3 on the side and just focusing on the derivative of x to the 4th. And we would get something like this. Now in our heads we might quickly compute this and get 12, but ultimately we're kind of holding that 3 to the side and it's not really a part of the calculation. We do the same thing with vector functions. All right, let's take a look here at property number 3. If you have a regular old Calc 1 function multiplied to a vector function, then you take the derivative by, well, what does this look like? Wait, this actually looks like the product rule, doesn't it? You take the derivative of the first, leave the second alone, leave the first one alone, take the derivative of the second. So property 3 here is kind of the extension of the product rule from Calc 1 when you have a good old Calc 1 function and a Calc 3 function. Okay. Property number 4 is saying, what if you actually had 2 Calc 3 functions, right? Like you had 2 vector functions, and they were dot product together. So you might want to take a note of that. This here is a dot product of these 2 functions. Well, actually, you get something very similar to the product rule. You get kind of like a dot product rule, if you will, right? It has the same basic format where you're taking the derivative of one, leave the other alone, and then flip-flop the order. The same thing actually holds true here on property number 5. This is kind of like the cross product property, where you again have that same basic shape. Property number 6, though, this actually operates like the chain rule from Calc 1, where you'll notice I'll have a regular old Calc 1 function plugged inside of a vector function. The way I would calculate that is take the derivative of the function, u, leave the inside alone, and then follow up with the derivative of that inside function. So this is very similar again to like when you have something like cosine of 2x. If you want its derivative, first you say, I'll take the derivative of the cosine part and I'll leave the other 2x part alone, and then I chain rule after. And since a lot of times we get something pretty simple out of the chain rule, or at least on occasion, we tend to write that in front, which is all that I've done here. Okay, so these are some of the properties for vector functions and other functions, regular functions that get mixed with them. But these are some really nice properties, and we'll be able to kind of practice a lot more with these in the worksheets. All right, there's one other property here, though, that's really important to talk about, and kind of an interesting property we'll come back to in a later section. Let's take a look at this theorem. Let's suppose that we have r of t that's a differentiable vector-valued function. It could be in 2 space or even in 3 space. But what if it was the case that r prime of t, or sorry, r of t, when I took its norm, when I measured its length, what if it was constant? Not constant necessarily like for any specific t, but like constant for all t, like no matter what you plug in for t, you always get the exact same answer back. Well, then we're going to say it's the case that my r of t and my r prime of t, if I dot product them together, I should get 0. What that really means, you might recall, is that if two vectors have a dot product that's 0, they must be orthogonal to each other. And actually, you can kind of see that happening right here in the picture, where I have an r of t and an r prime of t, and they're at a right angle. Well, I can guarantee you that that right angle is going to happen as long as I have a differentiable vector function and my r of t, its norm, happens to be constant. All right, let's take a look at how this would actually work. Like, how do I know this is the case? All right, well, let's take a look here. I'm actually going to go ahead and make use of a property that we just finished talking about. So I'll say here that by property 5 in the above theorem, we know the following. I'm going to go ahead and think here about how I can take the derivative of r of t dotted with r of t. So notice I'm doing a dot product here. And that is exactly what property number 5, sorry, I should be meaning property number 4, excuse me. It should be exactly what property number 4 in the above table was addressing, right? How do you do a dot product between two vector functions? And so we saw, oh, okay, this is kind of like the product rule from Calc 1. Okay, so what I would have to do is I would say this is going to be r prime of t dotted with regular old r of t, and then plus and reverse the order. So I would leave the first one alone, and I would end up dotting the second guy. Okay. Now what's kind of interesting here is to note that I can actually rewrite both sides of the equation here. On the left, or on the right side, what I notice is that I really have two of the same items, right? Remember, the order in which something is dot product together doesn't matter. So over here, I really just have 2 r prime of t, r of t, right? I have 2 of those. And again, there's a dot product here. I'm going to actually go ahead and write this a little more space so I can put in a full dot. And I'll even put some brackets around it, right? I have 2 of those dot products. On the other side, though, we can actually use a property that we saw very early on with vectors. If I ever have a vector dotted with itself, you might recall that I can rewrite this as the norm of that vector being squared. Okay, now this is kind of interesting. If I knew at the start that I was working with a differentiable vector-valued function, and if I already knew that this r prime of t was a constant, that is, r prime of t, its norm, is just some number, then think about what I can actually do to the left-hand side of this equation here. I can say, since r prime of t is a constant, then wouldn't taking that constant and squaring it still be a constant? But if I have a constant in there, if I want the derivative of a constant, that should just be 0. So I should just have that this whole thing here is really just 0. I'm really just using Calc 1 here. I have a number, r of t, its norm is just some number. I square it to get another number. The derivative of a number is 0. So what this tells me is that 0 is equal to 2 times r prime of t dotted with r of t. But of course, then I can divide by 2 on both sides, and that leaves me with the fact that r prime of t dotted with r of t must be equal to 0. Boom. So this is a really interesting property here. Again, it only works though if I'm dealing with a differentiable vector function and I have this r of t, that norm is constant. Okay? If I don't have that, I can't necessarily guarantee that there's a nice right angle that exists between the original vector that's pointed out the point and my actual tangent vector. If I was to go look at this in the 3D plotter, I can see this sort of behavior kind of happening or not happening in the previous example. Okay, so I've pulled up here the 3D plotter, and if I take away the tangent line that we put in here before, you'll see again that I have my blue vector here pointing out to a point. That's my r of t. And then this black vector was my r prime of t. And what you can see here is that if I was to try to look at, say, the angle in between them, I don't know if that angle looks like it's 90 degrees, right? It doesn't seem like it's a perfect 90. Those don't look orthogonal. But that's actually not surprising, because if you go back and you look at what we actually calculated on that last question for the norm of my r of t, you will see that we didn't get something constant. If I scroll back up to specifically look at that, what we'll see is that actually on the last example, we calculated over here, this r of t would be equal to this. And if I was to go ahead and actually calculate the norm of this guy, there's no way I'm going to end up with just a single number. I'm going to get something kind of similar to what we got here, which is going to be like a square root of trig function squared and like plus a t squared now. And there's no way that that's going to be constant. And since that's not constant, I don't really expect to see that 90-degree angle in there. However, if I did have something that was constant, I would expect to see a perfect right angle.